Hello everyone, and welcome to part 2 of our Simple Machines the Lever lecture. In part 2, we're going to talk about calculations. In other words, how can we use math to predict the amount of force or the amount of distance that are going to be put out by our lever. So first of all, we need to talk about a couple different concepts, which are mechanical advantage, ideal mechanical advantage, actual mechanical advantage, and efficiency. So mechanical advantage is a term that refers to how much something multiplies the amount of force you put into a machine. So how much does a machine increase your input force by? So if your mechanical advantage is greater than 1, then that means that it will multiply the force you put in. So if you put 10 newtons in and you get 20 newtons of force out, that's a mechanical advantage of 2, greater than 1. If you have a mechanical advantage of less than 1, then that means it actually decreases the amount of force. So if you put in a force of 10 newtons, you might only get a force of 5 newtons out. You calculate mechanical advantage one of two ways. One is ideal mechanical advantage, that I'm going to abbreviate as IMA, ideal mechanical advantage. And it is calculated when you're using levers by taking the input distance on your lever and dividing it by your output distance. Now, ideal mechanical advantage is basically what would a machine do if it was the ideal machine in an ideal world with no friction, no energy lost as thermal energy whatsoever, if it was 100% efficient. And so with levers, we calculate that with input distance over output distance. So if I had an input arm of my lever that was 3 meters long and the output lever of arm of my lever is only 1 meter long, then 3 divided by 1 would equal a mechanical advantage, or an ideal mechanical advantage, of 3. And if it was a perfect machine with no energy lost, it would multiply whatever force I put into it by 3 times. On the other hand, if I had an input force, an input arm that was only 5 centimeters long, but I had an output distance of 20 centimeters, maybe this is a pair of scissors or something, then my mechanical advantage is actually 5 divided by 20 is 0.25? Yeah, 0.25. I had to check my math there. So again, this mechanical advantage is less than 1. It actually decreases the amount of force I apply, but it would increase the amount of distance I applied it over. Okay, actual mechanical advantage then can only be found by actually measuring, using a lever or other simple machine and measuring the amount of output and input force, and it equals, if you flip this, the output force divided by the input force. So remember, these two are actually flipped. Watch out for that. So for ideal mechanical advantage, the input distance should be larger to have a large mechanical advantage, because you want a large input arm and a small output arm. But to get a large mechanical advantage, we want to be able to lift a heavy weight with a small force. In other words, we would want our output force, let's say we're lifting a 50 Newton rock, to be larger than our input force. So let's say we only have to apply a force of 10 newtons to lift it. That would be an actual mechanical advantage of 5, and would multiply our input force 5 times. And finally, we have efficiency. We're going to talk a lot more about actual mechanical advantage and efficiency later, but efficiency is basically a comparison of how close your actual mechanical advantage is to your ideal mechanical advantage. How much energy are we losing to friction? And it is equal to the actual mechanical advantage, AMA, divided by your ideal mechanical advantage, your IMA, times 100%. So, for example, if ideally my lever would have a mechanical advantage of 5, but it actually only took a 10 Newton force and turned it into a 40 Newton force, then what I actually got was my output force of 4 Newtons over my input, or so my actual mechanical advantage would be 40 over 10, which would equal 4. This would be my actual mechanical advantage, and that actually doesn't have units, sorry. So anyway, if my actual mechanical advantage is 4, but if there was no friction, if it should have been 5, then 4 divided by 5 is 0.8, which we multiply by 100% to get 80%. This machine would be 80% efficient, and we're losing 20% of our energy to friction. Okay, so let's look at these values now with some actual levers here. Remember, this would be the distance from the fulcrum to the load, and it would actually be to the center of the load. Here we'll go from here to the fulcrum. That's going to be our output distance. Our input distance would be from here to here. So let's say this is a distance of 30 centimeters, and this is a distance of 10 centimeters. Then my ideal mechanical advantage would equal 30, my input distance, over 10, my output distance, and I would have an ideal mechanical advantage of 3. And if I didn't lose any energy, it would multiply my force 3 times. Here's a class 2 lever. In this one, I measure the input distance is from the fulcrum to the input force. So let's say that's a distance of 40 centimeters. And then my output distance would be from the fulcrum to my output force, the load here. And let's say that's a distance of 20 centimeters. So my ideal mechanical advantage would be my input 40 distance, my input distance, sorry, over my output distance, which is 20, and that equals 2. My ideal mechanical advantage would be 2. So ideally, if I didn't lose any energy, if I put 10 newtons of force on this part of the lever, then I would be able to lift a 20 Newton force that's sitting where this block is. Okay. Finally, this is a class 3 lever. Here is my input force is now, or my input distance is shorter. This is my input, and let's say that is now 20 centimeters. And my output distance is again from the fulcrum to the load force, and let's say that is now 40 centimeters. So now my ideal mechanical advantage is my input 20 over my output 40, and that would equal 0.5. 1/2 would be my mechanical advantage. So in order to lift a 20 Newton block out here, I would actually have to apply 20 times 2 is 40 newtons of force in here. So here's one more useful equation that we can use. The input force times the mechanical advantage equals your output force. Okay. Now, we're going to look at this story problem, solve it, and that will be the end of this video. So, you are trying to loosen the lug nut on a car tire that is on very tightly. You use a wrench with a long handle where you apply the force 35 centimeters from the fulcrum. The distance from the fulcrum to the place where the force is placed on the lug nut is 2 centimeters. And it asks us, what is the ideal mechanical advantage of the wrench? Well, a lot of times with these problems, it helps to maybe draw a picture. So let's picture a lug nut wrench here that wraps around this lug nut and has a nice long handle. And it tells us that our input force, where we apply the force, so if we apply the force right here, then it's telling us our input distance is 35 centimeters. And it's saying that our output distance, which is from the fulcrum right here in the center, just to where it applies the force to the edge of my lug nut, that's just 2 centimeters. So my ideal mechanical advantage then is going to equal my input distance over my output distance. I always recommend showing your work like this, distance and distance. So it's equal to, your input is 35 centimeters divided your output by your output, which is 2. In my ideal mechanical advantage, 35 divided by 2 is 17.5. This would have an ideal mechanical advantage of 17.5, and there are no units on mechanical advantage. Alright, second part here. If you apply a force of 150 newtons to the wrench with your hand, how much force is applied to the lug nut? Remember, this is how much it multiplies your input force by. So we can say that your input force times the mechanical advantage equals your output. So if your input is 150 newtons and your mechanical advantage we're predicting to be 17.5, then your output force would be 150 times 17.5 equals 2,625 newtons. Okay, next part. If it takes 1,000 newtons of force to break the lug nut free, how hard will you have to push on the wrench? So we can use the same equation, input force times mechanical advantage equals your output force. And now all they've done is given us the output instead of the input. So input is going to multiplied by our mechanical advantage of 17.5 is going to equal an output of 1,000. So what would we have to put into this? I'm going to divide both sides by 17.5. My input would need to be 57.1 newtons. So I could actually lift a 1,000 newton force with a 57.1 newton force. Again, I can double check my work. This should be, I know that this input force should be less than the output force because I know I have a mechanical advantage of greater than 1. That checks. It all makes sense. Alright, so last problem here. If you move the wrench handle 40 centimeters, how far will the lug nut turn? So one other thing that we got to remember is that we don't get something for nothing. If you increase your force, you have to increase the distance that you apply that force over. So if I have an ideal mechanical advantage of 17.5, that means that the input arm must be 17.5 times longer than the output arm, and so you're going to have to move the input arm 17.5 times further than the output will move. So if you take 40 centimeters divided by 17.5, if you move the end of the handle where you're applying the force 40 centimeters, then the lug nut will only move 2.28, it looks like. No, 2.29. 2.29 centimeters is all the farther that the lug nut will turn. Alright, that's it for this video. Check in next time for more another video on our next simple machine.